Okay, so hello everybody and welcome back to our weekly seminars at BrIAS after a small interruption of a few weeks for the well-deserved vacation. So we are back with a very nice program in May, which will consist of several very interesting seminars and various events, among which I want to remind you the one on the 19th on critical underwater infrastructure and the conference on batteries that will be in the same week. But anyway, we can start today with two very interesting seminars. The first will be from Professor Paolo Falcone from the University of Modena Reggio Emilia and Chalmers University, who will introduce us something about cautious by design motion planning, the role of prediction. So Professor Falcone is an expert in the usage of MPC for various sort of mobile robotics, in particular for vehicles of various sorts. So I will not say too much more blah blah blah. I'm very happy to introduce him and to leave him the stage.
Thanks, Manuel, for the introduction. Thanks for being here, and thanks for the invitation to BrIAS. It's been very enjoyable so far. Okay, today I'll talk about the results from some research activities in collaboration with PhD postdocs at Chalmers and Unimore, but also in collaboration with companies like Zenseact, that's a kind of spin-off company of Volvo Cars, and based in Gothenburg, and Ericsson. Okay, so let's move on. Let's first introduce what motion planning is about. It's in an autonomous driving system, you have a stack, okay, where you have different modules in charge of perception, like context awareness, and a part of this stack are the route planner that you see over there, and path planner, which is what we are going to talk about in this seminar. So the route planner is what you have in Google Maps, in while ago TomTom or Waze or whatsoever, right? So you type in origin, destination, and you get a route, right? So a sequence of points you should follow to get from point A to point B, origin to destination. And that's basically the green line that you see over here. It's, you don't get any route which accounts for what your vehicle can do, right? So your vehicle might be a car, a bicycle, or can be an articulated truck, right? So a combination of long vehicles, but the green line doesn't know that. So that's why you as a driver, while following the green line, you actually plan in advance something like the red line, which is our path, right? You, from the red line, you extract some point which you try to follow, with that account also for what your vehicle is. So if your vehicle is a bike, probably you will follow the green line, right? But if your vehicle is a bus, that would be a tough job. So that's why you have, in an autonomous driving stack, you have a module called the Path Planner. That does exactly the job we do every day while driving our vehicles. Okay, clearly, we as a driver plan our path subject to a number of rules or constraints. So clearly, we plan a path and we follow that path subject to vehicle speed, right? So speed limitation, like the one that you see over here. Clearly, you don't plan anything which your car cannot do. So as a driver, we also plan our path subject to what the limitations of the vehicle are. Clearly, you want to avoid accidents. So if, while planning the path of your vehicle, you see a pedestrian or a static obstacle, well, you will make sure that you avoid any collision with any obstacles. Furthermore, you have limitations coming from the vehicle, right? So Here we have a steering actuator. Well, a steering actuator is basically essentially an electric motor, and you can't steer as fast as you want. So while planning your path, you should also account for limitation imposed by the physics of your vehicle. Same holds true for engine, braking, or whatever your actuators could be in the vehicles. So to solve this problem, to solve the path planning problem as I just stated it, in our community we offer a resort to a technique which is called the model predictive control. So the path, so the sequence of points which we plan to follow are the results of an optimization problem. So in this optimization problem, what we try to do is to optimize the future behavior of the vehicle with respect to a number of a future sequence of control inputs, steering command, acceleration commands, braking commands, and so on. So what we do is to have a plan, have a trajectory from the current time up to a future time instance. We just use the first portion of this plan, and we throw away the rest. We wait some time. We collect new measurements about the environment, about the state of the vehicle, its velocity, its position, and then we redo the same job over and over again. So this technique is called receding horizon or model predictive control. It's the same terminology, two different terminology for the same scheme. So let's try to write in math what we have just said. In our case, what we are going to do is to try to minimize every time instant a cost function. Such a cost could express the willingness of having a red line as close as possible to the green line, right? So please find a path which follows the desired route, such that I can go from origin to the destination. But then, as we said, our path must also be subject to the limitation of our vehicle, right? So we should account over here somehow whether our vehicle is a bicycle, a car, a motorcycle, or a truck. And then, as we said, we should also constrain the generation of our path to the limitation of the vehicle, steering limitation, steering rate limitation, and so on. And here comes something painful, a painful ingredient in this recipe, which is a number of constraints that model the collision avoidance against surrounding objects, other vehicles, pedestrians, bicycles, trash bin, parking car, everything that we would like to avoid a collision with. So here is some additional constraints that I'll come back on later on in the presentation. So the way these algorithms work is that the vehicle at the current time instant, so over here, plans the path such that it will slowly approach this, progressively approach this path over here, which is the green path we had before. So this is the future path, okay, that is planned to be followed. But at the next time instant, we redo the same job over and over again. So it looks like a scheme that perfectly fits the path planning framework, a path planning problem that we have just stated. But there are several issues to be accounted for. First of all, this is an optimization problem that we need to solve in real time. So what does it mean? It means that every 50, 20 milliseconds, we need to pack such a problem, give it to a software, a solver, optimization solver, and hopefully get the solution in time, okay, before the 50 milliseconds. But there are a few more issues. One is the stability issues. So how to make sure that the path we get is something which nicely and smoothly approaches the planned route. So we don't want to have something, that is oscillating or eventually deviating indefinitely from the planned route. So that's called stability issues. And there are results which guarantee such that you can eventually stabilize around the green line. So there are results requiring that you generate this green line such that this satisfies this system dynamics. It's a strong requirement. That's why in literature you find more recent results from us, but also a little bit earlier, allowing you to also feed this green line over here, which is not satisfying these constraints, and still have a stability guarantee. So, but what we focus on mostly in our work is feasibility issues. What does it mean? What is the feasibility issues? Well, what we want to make sure of is that we never plan a path such that a crash, for instance, an accident becomes unavoidable in the future. So we want to make sure that we always plan a path such that we can still do something in case, for instance, vehicles pop up, pedestrians suddenly cross the road, and so on, to some extent at least. There are results which allow you to make sure that this is the case, and in particular, you can design such terminal constraints, that is constraining the state at the end of the horizon, the position of the vehicle, the velocity of the vehicle at the end of the horizon. For instance, if you are planning to approach the wall, you may impose that the velocity in this position is 0, in such a way that you avoid smashing into the wall. That's just an example. What's the problem with these standard results that you find in the literature? Well, to cook such a set, to calculate such a set, you need to know the system dynamics, so this function f, no problem. Most of the time you have it, and it's fairly accurate. It's a model of the car, a mathematical model of the vehicle. You also need to know this set of constraints, no problem. Most of the time you know what the braking, steering limitations are to I would say, fairly accurate extent. But what you don't know is this constraint. Well, these constraints, once more, model collision avoidance, impose collision avoidance against obstacles that when you type, when you code your controller, well, they are not there. Nobody is going to tell you that in 50 meters you will have a pedestrian crossing the walk. So that's the problem with these standard results in control theory. So that's what we have been contributing with. And an example of how these constraints, unknown constraints, so these collision avoidance constraints could be modeled, are given now. So, for example, you can mathematically model the motion of the vehicle with this set of equations without going into the details. So what this model describes is the evolution of the lateral deviation from a path, for instance, from the green path that you have seen before, the orientation error with respect to this path. Here we can model the steering dynamics by using a variable, which is the steering angle, how much we are turning the wheel actually at the road. And these are the actuator dynamics. This is the longitudinal vehicle velocity, so how fast we are going. And this is the acceleration, the vehicle acceleration. Over here we have the commands to the vehicle, which is the gas pedal and the steering angle. That's it. So why am I am I showing this mathematical model? Because standard constraints on the vehicle motion are imposed by imposing constraints on this variable, these state variables and input variables over here. For instance, here I may want to constrain the lateral deviation of the vehicle from the green line. Why? Because on the right side it could be a sidewalk with a cycling path. On the left, well, it could be probably the other lane, right? So I don't want to have accident. Stay in the lane. That's basically what this means. So over here, I have other constraints, for instance, reflecting limitation from the steering actuators, the engine, and the brakes, the braking capability, and so on. Let's talk about these collision avoidance constraints, how we can build such a mathematical function, such an inequality. Well, in this, over here, this is just an example. You can do it in many ways. This is only one of the different possible ways you can write this inequality. So this could be a collision avoidance constraint, saying, for instance, make sure that the minimum distance, so here is written as a maximization, but it could be like as the minimum distance from a pedestrian is larger than something. So this means don't get close to closer to an obstacle more than, I don't know, or less than 3 meters or whatever. So this function clearly is function of the vehicle state and input. So it's function of the vehicle position and velocity, but it's also function of some additional variable that describes where the obstacle is. So this W, for instance, could be the relative position of the pedestrian, the other car, with respect to the vehicle. And clearly it's uncertain, right? So it's difficult to model what a human will do, whether it's a driver or a pedestrian. So the approach, for instance, we have followed is to model this, the motion of the obstacle we want to avoid as a dynamical system driven by a bounded noise. In the most general setting, you may also want to model the interaction of the pedestrian with the vehicle, right? So that's why over here we have also the vehicle states and control inputs. So an example that we have used in one of our publications is to model the pedestrian as an agent that follows this line on a sidewalk or along a crosswalk. So in this case, just to speed up, which is just a technicality, what happened is that we can describe a set of pedestrian's position at the next time instant, in 2 time instant, in 3 time instants, over all the prediction horizon. So basically, in our optimization-based motion planning, what we are going to have is a set of pedestrians' obstacle positions where we are not supposed to be over the prediction horizon. So that's the way you plan actually your path. So to make everything working, we need some assumption, as usual. Well, the first assumption we use is that there exists a safe set. Let's make some example. You are on the city center. A safe set could be, for instance, pulling over the car on the right. Clearly, such a set wouldn't work in the middle of an intersection, right? I mean, if you suddenly stop in the middle of an intersection, most likely you're going to end up in an accident. In a highway, that could be the same, right? So we assume that such a set exists. Clearly, that may not be the case. Well, in those cases, this approach doesn't work. There is a second assumption, which might be a little bit strong, but makes a lot of sense in practice. This is called the consistency assumption. What does it mean? So let's make an example of consistent prediction. So at time k, I make a prediction of where a pedestrian, this vehicle makes a prediction of where the pedestrian could be at time k plus 1, k plus 2, k plus 3, okay? So the red set that you see here describes the uncertainty, okay? Clearly, I know where the pedestrian will be in probability. Okay, so I make my decisions. I evolve of one more step. I'm now at time instant k plus 1. Still, I have to predict where the pedestrian is going to be at time k plus 2, k plus 3, k plus n. So this time I make my prediction. And this green set is, again, the uncertainty about this prediction at time k plus 1. And same meaning for this green set, same meaning for this green set. Consistent prediction is such that the uncertainty in a time k plus 1 is less than the uncertainty at time k. And that makes sense, right? So I'm predicting whether how the weather is going to be tomorrow. The closer I get to tomorrow, the less my uncertainty is. This is an example instead of inconsistent prediction. So you see that the green set is a little bit larger than the red set, okay? Clearly, this assumption might be broken. Think of I'm turning, okay? And suddenly I get my sun in the cameras of my vehicle. So I lose a sensor, I lose my camera, and then the uncertainty on my prediction is going to grow. That's unavoidable. Or I have a sensor failure, or suddenly it's foggy, or snowy. So there are many cases where such assumption could be broken. Okay, so let's see how all this works. This is some simulation. We are simulating a vehicle, negotiating this intersection with a pedestrian. So here we have a pedestrian, we have a crosswalk, and here we have our vehicle. So we formulate our motion planning problem as described before, completely disregarding whether the predictions we made are consistent or not. Let's see what happens. So what you see here is that I guess you can see over here, here you have two different colors. This is the sensor, the onboard sensor field. So we can detect the pedestrian over here. We cannot detect the pedestrian over here. So what happened is that, well, here there is no constraints, right? So we can go freely. But then suddenly a pedestrian appears here, and we have this surprise, right? So suddenly we are not allowed to get in that set anymore. Well, that's basically a case where the consistency assumption is broken. As a consequence, the vehicle doesn't manage to stop in time, and there is a collision. So you can see here from the lateral error, the orientation error, and the steering that the planner is also trying to do something desperate, right? Braking, but also steering. But yeah, the collision is unavoidable. So you see that here is the acceleration. This blue line is saying that the vehicle is making full stop, an emergency braking maneuver. No way. We have killed the pedestrian. Okay, but then the results we just gave us says that if our predictions are consistent, then we can avoid the accident. How can we make our prediction consistent? We have seen that just because of the limited sensor field of view, well, our predictions are not consistent. So what we do then is something which, as a driver, we do all the time. So here we have a crosswalk. We can see those pedestrians. But here, there might be a pedestrian that is there. We don't see it, but then suddenly starts walking. So what we do here is to drop some ghost pedestrian. And all the time, we assume that this ghost pedestrian is going to cross. Clearly, that may never happen, and we might be overly conservative, but that's what we do, right? I mean, if we see a parked bus and then a crosswalk, we are cautious, a little bit more cautious, right? We slow down. Why? Because someone may start crossing, but that's a kind of natural behavior. Let's see how it works. So over here, you see that we have a kind of ghost pedestrian, but we are slowing down because we propagate this set. So in this set, we are not allowed to be. This might not be the case at all, never. So the pedestrian may not show up over there, but actually suddenly a pedestrian shows up. Okay? So this is the predicted position. And you see here consistency applies, consistency holds. So in this case, we have all the time to slow down and brake in time to avoid a collision. Okay, so again, we are introducing a little bit of cautiousness in our planner to make sure that we can handle unexpected situations. So we have done tests with multiple pedestrians. So we have a pedestrian over here and a pedestrian over here. We can handle this type of situations. So those are this is a replay of an experiment that we have done. So in this case, we apply the same technique to avoid the collision with this pedestrian and with this pedestrian. So over here, you see the lateral error, so the deviation from the green line, the orientation error, the steering angle that we command, and this is the velocity. So we speed up, then we slow down to make our left turn. And at some point, we stop to let this pedestrian cross. But then we speed up again, and we see that no collision is possible with this pedestrian, and then we go. That's what you will see in the following animation, and then with the experiments. So here it's an important information, how expensive is in terms of computational complexity our approach. Well, this plot shows that the maximum time it takes to solve our optimization problem was 40 milliseconds, well below the 50, well, slightly below actually, the 50 milliseconds, which is typical for this type of application. So this is a replay of experimental data. Now you see basically the animation corresponding to the previous simulation results. So, well, this is the prediction of the vehicle. This is the actual vehicle. We plan that we should stop over here. The pedestrian has crossed. And then here, we understand that actually we can do the job even by left turning before the pedestrians come. And we do. This is Ivo. Now he's working at ZenseAct and is, well, is basically performing this test. So, yeah, here we used the simulated pedestrian. We didn't have the permission to do test with human pedestrians, as you can imagine. Okay, we have improved this approach. Why? Because, as I said, the consistency requirement could be a little bit strict, could be a little bit stringent, overly conservative. So, Yin Shuai is a postdoc at Chalmers, working in a project together with Ericsson, where we are trying to collect information from cells, communication cells, to learn and then predict the behavior of humans in traffic. And what she has done here is to assume that for some reason the consistency assumption is broken. So what does it mean? It means that the inequality, which I showed you before, is also with some positive term over here. So recall that this should be negative, minus g is a positive quantity, so this stuff is a quantity over here, positive quantity over here. So it can be shown that actually, even in presence of bounded inconsistency assumption, so what you can do is to solve an extra step optimization, so an additional optimization problem that is basically telling you how much you should relax some constraints, for instance, on steering rate, braking rate, in order to cope with such inconsistency prediction. So what we do, the idea is the following. Well, if possible, we try to drive smoothly and gently and nicely. But if something happens, well, we are allowed to brake more than it would be necessary for a smooth and nice driving. So, for those of you who are interested in the technicalities, I can share some paper. But over here now, I want to show you some results based on real data that we got by using this that we call the uncertainty-aware MPC based motion planning. So what you are going to see here is a vehicle that is driving on a highway. It's real data collected on the ring around Gothenburg. And at some point, while traveling on our lane, there is a vehicle that is cutting basically our path to take an off-ramp. Okay? So what is going to happen is that, well, the vehicle is driving with a comfort mode, okay? Very limited braking, very limited steering, to very limited jerk, lateral and longitudinal jerk, to plan very smooth path. But then at some point, we see that this guy, so the guy cutting our path, is behaving in an inconsistent way. And then the question is, how much harder I should brake or steer to avoid the collision with this inconsistent guy? That's what you're going to see. So here is the data that is publicly available from this ZOD. It's called the ZenseAct Open Dataset. It's very much similar to, for those of you who are familiar with WayMax, is the dataset released by Waymo. New plan, which is the data set released by, okay, it will come. So what you see over here is that this vehicle is suddenly, yeah, that's what it's doing, okay? So normally with the controller that we are using, we couldn't cope with such a cut and keep a safe distance. We recognize that we cannot. Then what we do is to switch to a controller which with different bounds such that the collision with this vehicle is guaranteed to not happen. So those are the results that you see over here. You see that the vehicle is braking as much as this, is allowed to brake as much as this, which I think is 3 meters per second square. But then at some point, we here we see this plot here shows the inconsistency of our prediction. So at some point, we detect that this vehicle that is overtaking on the left is moving suddenly to the right, so it's cutting our path. We recognize that our controller cannot do the job anymore. And what we do is to move to a different controller which is allowed to brake more. So in this way, we are allowed to avoid the collision with this vehicle. So in this version, we have just 3 different controllers. We have another version of this controller published in another conference. We don't know whether it's going to be accepted, where we basically have a continuum of controller. Okay, so we have found a way to solve the additional optimization problem very easily in time. Okay, so so far we have been talking about motion planning mostly in urban environment, and you have seen that the prediction, so the way we predict the behavior of the surrounding road users, play a central role. And you also have to modify the way you you solve your motion planning problem to cope for the uncertainty connected to the prediction of the surrounding road users. Now, at some point, what I was planning is to talk about how to make predictions of surrounding road users. But then I got, which is this part, which I can share, okay? But I will skip this part, because yesterday I got some slides from my student, who is, he has been part of the team of the Unimore racing, autonomous racing team. There are 2 competitions. One is called the India Autonomous Racing, that is done in US. Another one is called A2RL, which is done in Abu Dhabi. And this student has been in charge of designing the motion planning for autonomous racing. So yesterday he sent me some nice results. I thought it would have been more interesting and also more exciting to talk about results. That's why I will skip this part. For those of you who are interested, I can share the slides, but also the papers, and jump to this. Okay, so that's what we are going to talk about. The results are, the PhD student I told you about is Francesco Prignoli. He's visiting Francesco Borrelli in UC Berkeley, my former PhD supervisor, and he got also some help from some local PhD student. So it's a joint work. Okay, so what we've been focusing on is the following. So in racing application, you have, when it comes to overtaking, you have a right-of-way rules, which is extremely important. I mean, if the defender does not respect this right-of-way rule, he gets penalties. Also in Formula 1, it's like that, right? So if you don't give enough way to, enough space, lateral space, to the attacker, when the attacker is close enough to the defender, you get a penalty. It can be long lap penalty. Basically, you have to take a longer path, or you have to go through the pit lane. I mean, it's a punishment, right? Because you have broken a rule. So our question was, okay, if in the optimization problem we have seen before, also include those right-of-way rules, can we plan our path in order to be less conservative? Okay, can we take advantage of the knowledge of these right-of-way rules? So this is the question we are trying to answer. Why? Because in existing approach, what you do is the following. Well, there is another car you want to overtake. you know what is the best line, right? The shortest lap time path. You know that because it's depending on the track geometry. And what you do is to assume that the defender, the car you want to overtake, is just going to travel along that path at the maximum speed. Okay? So you completely disregard in some of the most common approach that this guy has to respect the right-of-way rule. Okay? Result, as you will see in a while, is that most of the time you abort the overtake. So you assume that this guy won't leave you enough space to overtake, and you abort. There are approaches which instead also try to model the interaction between the defender and the attacker, but this is done only in terms of collision avoidance. So what you assume is that the defender, so the car you want to overtake, it will only try to avoid the collision. But that's not the way it works in practice, right? Otherwise, you could just, point at the car, scare the car ahead, and here the driver will let you pass because, recognize that behind you have like a suicide path planner. And so what we've done instead is to code with a set of inequality, in the motion planner of the defender, the right-of-way rules, which basically says that when the distance, so the blue is the defender, so the car to be overtaken, the orange is the attacker, so the car that is overtaking. The rule is that when delta rho s, when the longitudinal distance is below a certain threshold, then the blue car should not decrease delta rho g, that is the lateral space. Okay? It should be from that point ahead, the lateral space left for the attacker should be larger or equal than delta rho g. That's the rule. It's one way of mathematically modeling the rule. So what we've done then is to model the defender as a vehicle that is planning its path with a model predictive controller, so exactly the way I've shown before, but we have coded the right-of-way rule. So we model the fact that the blue car is respecting the right-of-way rule. The orange car is planning the path consequently in a game theoretical scheme. It's a non-symmetric game because the blue car the only thing that the blue car does is trying to satisfy the right-of-way rule, while the collision avoidance is only in charge of the orange car. So it's an asymmetric game. Okay, so this is as I said, each car basically solve a very similar problem to what we saw at the beginning of the presentation. These two constraints are different for the orange and the blue car. For orange car, this one is a collision avoidance constraint, while for the blue car is a right-of-way rules. So it's a set of constraints which impose the planned path of the defender to satisfy the right-of-way rules. The right-of-way rules can be written as a number of inequalities made of continuous variable and integer variable. That's why the problem you solve over here is a computationally nasty optimization problem. It's a nonlinear optimization problem with the integer variable. Our goal is not at this stage to solve this problem in real time, is rather to answer the question, is really including the right-of-way rules paying off or not? Let's find it out. So here is, so far we just have simulations, so we don't have any on-field experiments. So what you're going to see are only simulations. So this is some simulation results, which shows you how the generalized Nash equilibrium problem, the generalized Nash equilibrium of this game theoretical problem is going to look like. So what happened is that, once more, this is the defender, this is the attacker. So here we have the attacker is close enough So this means that this guy over here that is following this racing line in green should leave at least this distance from the left lane boundary. That's basically the right-of-way rule as we introduced before. So what happened is that here is the baseline controller. So you see in this pale blue, what we predict is that the defender will just keep following the racing line. Why? Because that's the most convenient thing to do, right? If you want to be fast, you just follow the racing line, which by definition is the minimum lap time racing line. Okay? So if this is the case, then the attacker try to see if there exists any trajectory such that he can overtake the defender. That's not the case. So if the defender goes on the racing line, there is no way to overtake it. Aborted. So that's what happened instead by using our approach. So you see that the blue vehicle is following the racing line, but at some point it will see that the attacker has approached and it has to, the right-of-way rule must be satisfied. So it will deviate from the racing line, leaving enough space over here such that the attacker can overtake. So that's, I hope it's working. That's a simulation. So let me pause over here. So this is the baseline controller. Again, we just assume the defender is following the racing line without caring about the attacker, neither the attacker nor the right-of-way rule. Here, that's not the case. So what we are counting here are the overtakes compared to the number of possibility to overtakes. And since usually we overtakes in curves, in corners, that's basically the number of overtaking maneuvers over the number of overtaking possibilities of number of curves so far. So at this stage of the simulation, so with our approach, we have overtaken 6 out of 6 times. Clearly, sometimes we will also fail. Here, with the baseline approach, we have aborted all the times. So what you will see is that as the two vehicles travel along the track, those two numbers will increase. But clearly, not surprisingly, over here you will see that the success rate in our approach is much higher. So the yellow stripe is basically the space that the defender is supposed to leave according to the right-of-way rule. So on the left, you see that that space is not left. On the right, it is. And you see that over here, we have aborted all of the 18 or 23 now possibility to overtake that we had, while here we are at 22 over 23. Only once we had to abort. Well, it will go over and over again, and the outcome is that we succeeded in 93 out of 100 trials, while the baseline only makes 45 overtakes, successfully makes only 45 overtakings out of 100 possibilities, 100 corners. Okay. So I would close here my presentation. So most of the stuff that you have seen has been funded by the VASP, which is a research program in Sweden that stands for the Wallenberg Autonomous System Program. Wallenberg is a family, rich family in Sweden, funding this nice program since 2015. And is also partially funded by Vinnova, which is the innovation agency in Sweden, funding applied research together with companies. In this case, Zense Actes, and Ericsson. And also some of the stuff that you've seen here has been funded by the Swedish Research Council. And yeah, those are the people I've been working with in the project that you have just seen. do I have more time or?
If you want, yeah.
How much is, because I have changed my plans and.
We have never stopped people historically, so if you have something interesting to show.
Yeah, I will be super fast. Just to give you a taste of what we've been doing when it comes to prediction. Is the part which I skipped to present this newer material that I received last night. Okay, so we are also working on the problem of how to make predictions, how to predict the behavior of humans in traffic. It can be highway traffic, it can be urban traffic. How is this done typically with nowadays with neural networks, of course. But what's the problem with neural networks? Well, the behavior, the prediction of how the traffic around us is going to behave, you have seen will going to end up in our optimization problem, right? And so basically the G function, the G inequality, G less equal than 0 inequality you have seen before. Well, the problem is that if you plug a neural network there, our problem is going to get quite nasty to solve. And just to give you a number, there is a famous paper out there, which is the kind of benchmark for predicting the behavior of road users, that is made of 500,000 parameters, a neural network with 500,000 parameters. Not really a nice object to have within an optimization problem. So that's why what we are doing is to try to solve this problem with prediction tools which have a more friendly mathematical structure. Let me show you what I mean by that. So we are using tools which have been used in opinion dynamics. Opinion dynamics are those mathematical tools describing, for instance, how preferences in networks develops depending on the influence with others. It can be Facebook, or it can be another social network, or it can be just a community. If we start a discussion over here, depending on the trust, we have the influence that we have between each of us, then some opinion will propagate in this community in different ways. So what we've done is try to explore if those tools can be useful to model the behavior in a traffic scenario. What in this type of tools, what you do is to model a single individual in a traffic scene as a Markov chain. And what you can do then is to form a network of Markov chains to also model the interaction between these Markov agents. Is that convenient? Well, yes, from one point of view. Why? Because if you describe with those pies the probabilities that an agent will make a decision rather than another one, then the evolution of these probabilities is described by this very nice system of linear differential equation, where you have some the elements which are on the main diagonal that describes what is called the isolated behaviors. So if I'm a pedestrian, I'm freely walking in the night in a city. There is no car or no other pedestrian around. What's the probability that I keep walking on the sidewalk rather than crossing the road? Well, it's basically just a statistical measure. I can just count the number of times a pedestrian at the time crosses or keep walking on the sidewalk. But then what happens is that you have also off-diagonal elements which describe the influences. So how likely is that I make this decision given that, for instance, Emanuele is making another decision? So if you properly define the decision space, that could be keep on walking on the sidewalk, crossing, or any other things. For a car, it could be go straight, turn right, turn left. Then you can describe to some extent the behavior of a traffic scene. What's the drawback? Well, the drawback is that the complexity of this, so the number of states in this mathematical model can very rapidly explode. So if the decision space is quite large, then this mathematical model can reach dozens of states very quickly. There are tricks you can place, marginalization or other things, but still, that can be a problem. So what we are doing now is trying to calibrate these matrices over here. So this is the linear dynamical model that I tell you is going to describe the behavior of this network of Markovian agents. So those are, so one of these metrics describes what is called, again, the isolated behavior, but all these two matrices define the interactions, so attractive and repulsive force. In principle, there are tools out there to identify, to calibrate those matrices from experimental data, but that's actually what we are working on. So we are using some data from simulators to calibrate these matrices and be able to use these model structures in our motion planning, optimization-based motion planning algorithms, which we have seen before. So that's what we are doing on this side, on the prediction of road users' behavior. So I will stop here. I also have some additional work slides on this topic in case some of you are interested, but yeah, I will stop here to be more concise. Thank you.
Okay, so thank you, Paolo, for your presentation. I imagine we have time for a few questions, so we start from the back.
I can shout out if you hear me.
No, but they will not hear you online.
Thanks, Paolo, for the nice talk. Every time I come at BrIAS, I remember why I choose biology. I know that 4 of you will be funny this one. I have 2 small questions. One stupid, and one less stupid. You choose which one is it, the one.
Let's go for the stupid one.
You choose.
Yeah.
I give you the question. So first, you always indicate the object in front of you, or in the case of attacking a car that should leave you the space. But what about considering the object behind the car?
That's not stupid at all, believe me. The project...
No, wait for the second question.
Okay, but then it's scary.
You might choose...
This was the stupid one. Yeah.
The other one is I know, biology side. Have the community ever considered the fact of, sort of social behavior and cultural behavior when it comes to different parts of the world? I mean, my mother always told me, if you are crossing the street, come back if there is a car approaching. My father say, no, keep running. And I don't know if, this is Italian or European things, or you're in Sweden testing these things. The Swedish are maybe educated in a certain manner to keep straight walking. Or maybe if you go to Asia or if you go to South America, they might rather jump, or I don't know.
Yeah. Okay, let's start from the first. The first question is not trivial at all, actually. And with the Zense Act, the project we have right now, what we are doing is, so what we've seen is that in these data sets, so data from real world, okay, it's not fake artificial data. What we have seen is that some of the autonomous driving benchmark, they do really things which would annoy most of the drivers, like changing lane, okay, without recognizing that the car behind is coming at high speed, probably to overtake. And that could be very dangerous. You could also trigger an accident behind you, okay, just because you have not seen this. Don't consider extreme case like a collision, okay? It could be that you scare the driver that is coming from behind, and you trigger an accident 100 meters behind you. You are not involved, you have not collided, but still you are responsible for the accident. So what we are doing with Zense Act now is the following. It's still about prediction, because what we are trying to do is, if I plan this at time t+1, what the vehicles around me are going to do? Nothing special. Okay, let's keep planning. What if at time k+2 in the future, I do this? What the other vehicles are going to do? So it is called closed-loop prediction. You can do it, so you can predict what to do, also based on the reaction that vehicles around you will have based on what you do. You can formulate such a problem rigorously, actually, as we have done also in the autonomous racing, but it's super complicated to solve. I mean, you need a supercomputer, and clearly it's paying off. We know that, okay? But then now the challenge is to do it fast enough to do it in real time. So yeah, the topic is I would say is one of the hottest topic in prediction in autonomous driving nowadays. And then when it comes to the second question, that is remind me. Sorry, I was. Yeah, right. Yeah, that's also a sensitive, I mean, a special problem, because just to give an example, we were approached by an Indian company, and what they wanted to do is to make an adaptive cruise controller system for the Indian market. Okay, it's a simple system. It's a system that we have here since I would say late 90s. But none of the suppliers like Bosch, Continental, is going to deliver the product down there, because the certification system is completely different. I mean, the traffic is so much different. And again, we are talking a super simple system, adaptive cruise control. You know what it is? I mean, it's keeping drive at some speed, and then it will slow down if there is a vehicle in front of you. Way, way simpler than autonomous driving and blah, blah, blah. Okay? But still, for that system in the Indian market, they say no. So they will probably sell some license, but then the responsibility is from a local company. I'm not aware of any way of commercializing easily such a complex system in multiple markets, to be honest. I know that everyone is aware of the challenge, but to be honest, I'm not aware of any easy solution of this problem. Thank you.
Thanks for the nice talk. And sorry to make the classical question, but you showed before a mixed integer nonlinear programming problem. What's the average computational time for that?
Well, I don't know. I mean, I didn't really. We didn't even write in the paper, because again, it was not really the focus. But I guess I would say like probably even some dozens of seconds. Like it's a small problem, but quite many integer variables. So I would say it could be easily 20 seconds. Yeah. But again, I can double check. I can ask Francesco. I'll let you know if you're interested. Yeah.
Right. This was just for my curiosity to see what's the gap between the.
I would say it's a large gap.
Yeah.
Yeah.
So in your opinion, clearly this is not something we're gonna solve in the next 5 to 10 years using MI and OOP. What's a possible future approach?
A common approach when, for instance, we have used when we do like this uncertainty-aware controller, when you have this unexpected behavior, and so we have to solve an additional problem. It's complicated, and what you can do is to approximate the solution of this problem with a neural network. And we have seen that when you solve the exact problem, the computational complexity can go up and down depending on how complicated is the traffic scene. When you use the neural network, the computational time is constant. It's pretty much constant. Clearly, if you have not trained well or with the right, whatever it means, data set, then the solution that you calculate with the neural network is going to be wrong. But that's one typical way of doing it. I don't know how easy it's going to be for this mixed integer problem, but this is probably something that we will try.
Thank you very much for a very nice talk that touched upon many different areas. Just to follow up a little bit on this idea of game theory and the generalized Nash equilibria, so there is also a cost function there.
Yes.
And one of the criticisms of a game theoretic approach is that you need to know the cost of the opposing players. Is the cost kind of this attacking, defending framework is pretty well known or pretty well formulated?
I mean, right now, I mean, in this context, I would say it's easy to guess a cost because the defender will try to stay as close as possible to the racing line. But now one could think that the same idea could be applied also to a urban environment. And then what is the cost? That I don't know. I mean, it would be a little bit more difficult to guess because it would be like guessing, first of all, the reference path. Yeah, but then we are back to the previous problem. Is the car in front of us going straight, making a left turn or a right turn? So I would say that my answer would be, safe answer would be that in some cases it's easy to guess, in some other, no, not at all.
So, but it seems like this setting of racing is actually, you could probably argue that you might know the cost function of the opposing player better. How long is your kind of prediction horizon in terms of seconds in this?
In terms of seconds, I think 1.5, if I'm not wrong.
1.5 seconds.
Yeah. At least this is what we started from, yes.
Thank you.
Okay, so I propose to thank again the speaker and so thank again Paolo and then to go for our usual coffee break before starting with the second seminar. As usual, you are warmly invited to approach Paolo, make him all the remaining questions that you have, and to start discussing, and then see you back in around 10-15 minutes after a coffee for the second talk. Okay, so welcome back everybody after a nice and well-deserved coffee for the second seminar of today. So it's really my pleasure to introduce Professor Hideyuki Sawada from Waseda University. So Waseda University is one of the key partners of ULB University around the world. There are several collaborations ongoing, and Professor Sawada has been here with us for several weeks, collaborating and chatting around with various groups. And I'm very curious to look at his presentation. It is about robotics and machine learning techniques for understanding, controlling, and predicting physical phenomena. So I leave him the stage, and thank you for coming.
Thank you very much, Emmanuel, for the kind introduction. Okay, my name is Hideyuki Sawada from Waseda University. Okay, today's my topic is this one, robotics and AI. And firstly, I briefly introduce Waseda University. Our university is situated in the middle of Tokyo, and you see, yes, and Tokyo is here, and Osaka, and currently Osaka Expo 2025 is going on. And the Waseda is here, and this is a map in Tokyo Metro, and you see here, this is Tokyo, and our Emperor's house is situated just next to Tokyo Station, and here Shinjuku. You see in Shinjuku Station, every day about 3.5 million people are using this station. Yes, in the station, and the Waseda University is situated just close to Shinjuku. There are only 2 stations, about 3 minutes from Shinjuku. Oh, okay. I see. I have to use. Oh.
Yes.
Well, maybe this microphone.
No, please use.
This one?
No, please use the.
Oh, okay. This one.
Yes.
Okay. I see. Okay. Yeah, I understand. Okay. Yes, the Waseda is here, and our campus is directly connected from the subway station. Just get to the station from Shinjuku, only 3-4 minutes, then go up, then my building. Yes, and Waseda is a university, a private university in Japan, and leading university, especially specialized with robots, human-sized robots and robots. And we have about 40,000 students in undergrad and about 10,000 students in graduate school. And so far we have many prime ministers in the alumni of Waseda University, and also business leaders and CEOs of in big companies in Japan, like Sony, Casio, Lotte, ANA, Honda, and so on. And we have some rankings in Japan, not in the world, in Japan. And we have the first one in Japan in many subjects. And also we have many collaborations in all over the world. And you see in Brussels, ULB, we have our university has a Brussels office in ULB. And we are encouraged to have a good collaboration with Belgian universities, especially ULB, VUB, and so on. Okay, and here about the history of robotic research to be conducted that have been conducted in Waseda University so far, and more than 50 years ago, Waseda University invented a human-sized biped robot, firstly in the world. The robot. I will show you the demonstration video later. And then in 10 years later, we again introduced a piano-playing robot like this. And it was exhibited in Tsukuba Expo, held in 1985, 40 years ago. And after we started a humanoid project for the development and research for human-sized robots to support and to work with. And so far we have developed many kinds of robots so far. And this is some robots that have been developed in our university until 2000. And then later in the 2000, okay, yes, maybe, okay, maybe this one, okay. Let's, oh, no sound. No sound. Oh, okay. Yes, this is the first robot to maybe, yeah, like this one, 50 years ago. The first robot 50 years ago that we have developed is the static walking robot. It means that in each small motion, the stability is calculated. Then in any situation, the stability is robot was kept under the control. But this kind of stability, static state walking is different from us human walking, because we are walking like this dynamically, right? So we cannot stop on the way of the motion, right? So you fall down. Then, but firstly, the first robot was realized by the static motion one by one. And at that time, the robot took about 30 seconds for one step, because we need some calculation one by one. And the first robot used the hydraulic system, right? Not the electric motor. At that time, there was no such motor, right? Then, and the second one, that was developed in 10 years after that, we realized the dynamic walking, just introduced here. Maybe not this one. Okay, like this one, dynamic motion, walking motion, like human, and also it can climb, a little bit climb up steps and some slopes, like this, more than 40 years ago. And after, we developed a piano-playing robot by using DC motors, with maybe 30-some or more, DC motors for the control of the fingers and the feet for playing keyboards. And in Tsukuba Expo in 1985, this robot co-played with the real orchestra. Maybe we are like this one. It was really a sensational work realized by robot 40 years ago. Yes. Yes, right. Yes, this is an old video, but this is the history. Okay, then in 2000, we started another robotic research institute called Future Robotics Organization, and we have developed further robots, not only just to walk or make move, but to handle some objects or to make a collaboration and a communication, including touch with human. And this is a video of a robot about 10 years, developed 10 years ago, around 2010 something, sometime about 10 years ago, and it can dexterously manipulate the small stuff. It is a chopstick, and it can handle it to. No, it is not a chopstick, but a straw. To put it in a cup, to give it to another person, right? And also, this robot is able to break an egg, maybe this one, like this. Yes, dexterity, yeah. Like this, maybe like this, okay. By controlling the force given to the eggs, it can softly. The robot is able to softly grasp the egg, and also it gives some force to break it on a pan. Okay, right? And yes, the robot, the walking robot. As you know, these days there are different kind of or a bunch of robots introduced by the U.S., of course, in Japan and also China. But as I introduced, the first biped robot was developed by Waseda University, and these days the different kind of robot is developed. But we Waseda, group do not work for biped robot anymore because this is a typical structure of the biped robot. The biped robot is expressed by the physical control model of an inverted pendulum, right? Then all the motors are settled in the inverted pendulum, but it is much complex, but it can model like this. Then by modeling all the models and the geometrical structures of the robot, we can construct a control system. Then once we get a control model, it is not difficult to control it. What the problem of these days is the power of the motor to generate power. It is because, have you ever think of how much force is given when you walk? For example, 60 kilograms person, when you walk, how much force is applied to, for example, in a knee? Have you considered that? About 4 to 5 times of your weight. This means that the 60 kilogram person, when he walks, about 200 kilograms force is applied to the knee or of the foot. Then to make a similar motion by a robot, the motor in the knee or the ankle has to generate such strong force and real time. But luckily, it is possible to obtain such motors thanks to the development of the motor companies. Then these days, this kind of biped robot is able to make a pretty quick running motion or jumping or something much complex. It is, of course, it is the real results of the control systems of the feedback of motor systems, but also the development results of the pretty strong motors to generate force in real time. But we have developed, Waseda University have been engaged in the development of such robots so far, and these days we are much interested in the further flexible robot to be able to have a good communication with human. Yes, for supporting or having interaction in real time with a human, like to give to hand some object to a person or to work together or something more. Okay, as you know, robots have been firstly introduced for the manufacturing in factories, right, in a secondary sector of industries. And then such robotic technologies have been introduced to primary sector of industries, such as agricultural robots, or agricultural workers supporting robots and something more. And also, these days, such robots have been further developed in the tertiary sector of industries as a service robots to support human or to assist human and something more. And this is another result introduced by the graduates of Waseda University. It is a project called Gundam Global Challenge. Gundam is a very famous robot, firstly animated in Japan in 1970s, almost 50 years ago. And all Japanese people know it. And about 10 years ago, we started, the company, animation company, and some companies got together, including the graduates of Waseda University, alumni of Waseda University, to develop the real-size Gundam robot. The Gundam robot in the animation, it is introduced as a 10 times taller, 10 times size of human, and it fights with enemies, right? And then we started a project to develop the real-size Gundam to move, not only a statue, but the move. Okay, right? Yeah, this is a result. the robot was introduced to open public in 2021. In fact, the robot has been, this project started to introduce this robot for the Tokyo Olympic Games to be held in 2020. But due to the corona situation, it was extended 1 year later. Then the robot was open to the public in 2021, 4 years ago. Okay, this one, it moves. Okay, you see, these are the people. Yes, 1/10 of the robot. And they observe the robot from the top. Okay, the height is 80 meters, as introduced in the animation, and the weight is 25 tons. Because, if person with a weight of 60 kilograms, when the guy becomes 10 times taller, what will be the weight? The calculation is cube, right? 10 times, 10 times, 10 times, 1,000 times heavier. It means that if 60 kilograms person, if he becomes to 10 times greater, the weight should be 60 tons, right? As you know, we human beings do not have motors to generate such great, amount of force, right? So we did something to realize it. Okay, yeah, this is a robot, and it's me. And he's a doctoral student in my laboratory, and this is the size of the robot, and you see the robot moves like this. Yeah, this is a demonstration of the motion of the robot. It moves very slowly because each motor has a great amount of gears to amplify the generated the power into the outputs, right? So the gear make the motion slower in proportional to the gear ratio, So the motion is very slow, but it moves. Even the hand part, the robot is raising his arm like this. But the weight of the arm itself is several hundred kilograms. So this means that, and also it is just the weight. But if you make it if you make the arm go up, then the motor of this part works. It means that the force to be given from this motor has to be calculated with a moment, right? Proportional to the distance, right? So the force should not be only the weight, but also the torques. So the several times of the several hundred kilograms. So like this. Yes, pretty heavy arm to be going up like this, but it works, right? And the Gundam has been exhibited in Yokohama, next to Tokyo, from April 2021 until March 2024, just until 1 year ago. Then, in March of 2024, we disassembled it. Then what happened? They were sent to Osaka Expo. Okay, here. And currently, this robot is exhibited, not moving, but it is exhibited like this, in a still pose like this, in Osaka Expo. So if you go there, you can see the Gundam, but the real size Gundam, 80 meters height, but it won't move anymore. Yeah, like this. In a pavilion, they exhibit the Gundam. Yes, and then in the pavilion they present some metaverse exhibition in this one, so that you can observe the Gundam only in a 3D or something in this pavilion. Yeah, and the outside they exhibit this Gundam. Okay. Yeah, currently until maybe September of this year. I don't know. Yes, maybe 3-4 months from April, this month. No, last month. Yeah. Okay. Then, okay, so far in Waseda University, different type of robots has been introduced so far. And we have realized that the robot in factory can be, sent out to home for open public, so that it can work with human in a human living environment. And then such robot cannot be specialized with great power or fast motion or something more. They are not. They will not exist. They will not exist for fast production, mass production, or very precise motion or something more. Instead, the robot should behave like human, because we human do not move such precise, such fast. But to work or to live with human, the robot should be like human, right? And so to do so, the one approach to be installed in robot is machine learning or AI, so that the robot is able to learn the communication skill under the learning with human. And also the robot can learn the living environment like a human baby do, right? Human babies are born without knowing anything. But by making an interaction with his or her caregivers, I mean the parents, they get to understand the living environment, world, and also communication skills to handle in the surroundings. So we expect robots to behave like the human, right? To do so, we are trying to install good AIs or machine learning techniques in robots. Okay, yeah, the AIs, artificial intelligence, it is defined like this. It is human-like intelligence realized by computers, and it was first introduced about 80 years ago as a neural model, and then the AI or artificial intelligence was firstly invented or defined by in a Dartmouth workshop in 1956. And then after the introduction of the perceptron, the ability of the machine learning has been greatly increased. Yes, and then now we have pretty good machine learning techniques these days as a deep learning and something more. Okay, and this shows some brief story of artificial intelligence. And then, yes, in Japan we have, mainly so far, Japanese professors and researchers have been contributed rather theoretically and mathematically for the construction of the mathematical model of the machine learning so far. And Professor Oteru is my supervisor on my college studies, and he already passed away. And I started the research of AIs from the mid 1980s. Yeah. And okay, then why the machine learning techniques works pretty good? Okay, I show you one example. Here, suppose that we have one picture over full HD. The full HD has the pixels 2K multiplied by 1K, right? And each pixel has 8 bits and 3 colors, right? So the total amount of information given by one picture is 8, here, about 50 megabit, right? Then if we consider 1 second moving picture with a frame rate of 30 frames per sec, then the total amount of the information to be transmitted from 1 second full HD movie is 1.5 gigabits. Wow, great amount. Then we can calculate how many possible moving pictures can be made by this amount of information. We can calculate it. 2 to 1.5 giga, right? This is a calculation. Possible pictures, moving pictures of 1 sec video, right? It is this variations, great amount. You know, for example, in the comparison, number of atoms in the universe is approximately is 10 to 80, much smaller than this one. So you have a picture, but the possible number of the pictures is this amount, 2 to 1.5 giga, great. So the difficulty of understanding picture is not easy. Before the deep learning, many information scientists has been trying to construct very good algorithms for understanding some object in pictures. But we recognize that there are pretty big difficulty for flexibly understanding what is described in a picture or moving pictures. But thanks to the machine learning, especially deep learning, and these machine learning techniques, the machine learning works pretty good for understanding, especially pictures and also auditory signals and something more. Okay, then this shows the comparison of the brain and the computer. Here I show some capacities of human brain and the computers. And it is said that in human brain, we have about 100 billion neurons and 30 trillion synapses. On the other hand, in the recent PCs, we have about billions of RAMs and also trillion bytes of terabytes SSDs, right? And somehow these, from the viewpoint of the calculation capacity, the number of the neurons or bits are almost equal with each other, right? And the element size is mostly the same, and the energy consumption is also not a big difference. But what is interesting is that in the case of a human, as many as we use our brain, the temperature is kept around 36 degrees. It won't go up to 40 degrees or something. On the other hand, in the computers, if you make a very good calculation like deep learning, calculation learning, and the pretty difficult calculation, the temperature goes up for gridding something. It means that the computer CPUs works good, but on the other hand, most of the powers consumed by the calculation is radiated as a heat. This means that the efficiency of the calculation of these computers are not very good, like human or biological systems. And also the other things for communication or data translation or transmission, we have pretty different methods we have. The biological system has a parallel processing. On the other hand, in the computers, the computers these days, we use the serial computation, but by increasing the number of clocks, right, with several gigahertz. So it means that it can make a calculation about tens gigatimes per sec. And by increasing this, the clock speed, we can make the calculation much faster. This is a basic, idea for these calculation. But these are different things. So by, realizing if we can realize some, new method to work as biological systems, we may be able to realize much better, calculation machines in the future, I expect. Yeah, okay. Yes, the neural network, the structure of the neural network is something like this. And it has multiple layers like this. And in each layer, we set cells for the, transmitting information in each layer. Why? It is because this model rehearsed to human neural model. Human neuron is constructed like this by accepting some, the ionic information from the other cells. Then the potential of the neuron potential in the cell body is working, and then once it exceeds some threshold, then output is gone to the next one. So this, the behavior is replicated in the calculation system as a neural network, like this. Okay, this is a simple model of a neuron by accepting plural inputs from the other cell. Then when the threshold, the internal potential goes up, exceeds some threshold, then output comes out. Okay, with this structure, this is a pretty simple structure, but what is interesting is that by using this structure, we can construct logics as we use in computers like this. For example, in AND operation, okay, here the weighting function WIs can be given to this one. In the case of AND, okay, when the input can be 0 and 0, and the 0 multiplied by 1 plus 0 multiplied by 1 equals 0, then it is less than 1.5, then output should be 0, right? And then in the case of 1 and 1, then this value can be 2, then the 2 is greater than 1.5, then output should be 1. Then, logic can be defined like this. Okay, here, we can set the two inputs in the x-axis and y-axis. Then AND operation can discriminate these three states and this one state. On the other hand, OR operation is to discriminate this one state from the three states, like this. Just discriminate the status in a linear line, like this. Then, what about exclusive OR operation? Exclusive OR operation outputs 1 when these two inputs are different, right? So it means that the exclusive OR operation to discriminate these two from these two, right? In this case, there is no line that discriminates these two states, right? But, the exclusive OR logic can be realized by using three cells with 2 layers. Okay, this can be one layer, and this can be the second layer. By connecting, multiple cells in, plural layers, the exclusive OR logic can be realized like this. So this means that any logic can be realized by the neural models. And as you know, computers these days can make any calculation by summing up the logics. This means that by accumulating the neuron cells in plural layers, it can execute any calculations as computers are doing, right? Then neural network has been introduced like this. Then in this structure, what is the problem is how we obtain the weighting functions to connect each layer, right? Then about 40 years ago, the back propagation algorithm by Lamelhart was introduced. Then the neural network boom came, right? This is a mathematical calculation. No, maybe this one. This is the mathematical calculation. Okay, this one, yeah. 2 layers like this. It is just a calculation. So you can write a code in a computer. So then the weighting functions can be easily calculated to associate input vectors with the output vectors. Yes, this is what we expect. Yes, right. The neural network can be any nonlinear function, yeah, to associate input vectors with output vectors, right? Then what we have to do is to obtain the weighting functions to connect each layer, right? Then calculation can be made like this. Okay, maybe I skip it, right? And these days, the deep learning works pretty good, but the calculation amount is great amount. Like these days, for example, ChatGPT. Maybe I will present this later. Usually we set several thousand layers, right, for the structure, and in each layer we have multiple cells with the several thousand layers, right? And in each layer, the weighting function among them can be calculated by the deep learning calculations. This is the recent progress of the neural network, and yeah, we have a pretty big boom of deep learning these days, and deep learning was firstly introduced by Geoffrey Hinton in 2006, about 20 years ago. Yeah, 20 years ago. But this network was firstly introduced by Professor Fukushima in 1979 in Japan. Yeah, he's still a researcher. He's 90-some years old. He's still doing research. Yes, he introduced in 1979. He introduced neocognitron. Yes, and what he has introduced is that he refers to human vision system. Okay, by introducing two different cells, which is called S cells and C cells. Okay. S cells works for feature extraction in pictures, because he refers to the human vision system, okay, feature. And then C cells works for pulling of the response to sum up, to make some groups arbitrarily, to make some meaning or sense by the combination of the features, right? Okay, maybe this is the example. Okay, these are the pictures introduced in his paper. Maybe I forgot to write. Okay, yeah, yes. In this paper, neocognitron. Okay, here, for example, A, the character A, it has some features. In his network, some feature, the characteristic shape can be automatically obtained by the C cells, like this, right? S cells, right? Then the C cells works to make a good combination to express some, in this case, A character by the combination of the, feature shape of the in the S cells, like this. Then the network outputs that this drawing is read as A. Right? Yes, he proved at that time, 1970s, he introduced this structure of the network mathematically, and he presented the pretty effective performance of the neocognitron at that time. But unluckily, at that time, the computer power is not enough. So he had some limitation of the calculation. So at that time, we didn't have a big boom of the neocognitron. But somehow, in 2006, about 30 years later, the deep learning referred to neocognitron, the structure of the C cells, S cells and C cells. Then, thanks to the computer powers and the big data, found in a network, the network is able to accept uncountable number of data with the quite great number of layers, then the performance of the neocognitron structure works pretty good, they proved. Now we have the big boom of the deep learning. And also, we also have a large language model called LLM. Then large language model is expressed as a series of conditional probabilities. Then this LLM model predicts the next word from a sequence of text. For example, when we have some sequence of the capital of France is, then Y should be the answer. By deferring to the learned data that has been made by having a great number of inputs of texts, then the network answers Paris, right? And yes, the LLM works like that. And it is said that the GPT-4 has been trained with more than 10 trillion words. Yes, word set. It's pretty great, thanks to the computer powers and the network and the structure of the computers and the internet. Yeah, it works. Okay, then okay here, but okay. So what we should be noticed for AIs is that the energy supply is assumed to be infinity. The calculation and the learning and the calculation of the AIs require quite great of electricity. And so far, the energy supply to AI is consumed, is assumed to be infinite. And also, computers cannot be created without computers. We need computers for making computers. And also, even a logic, semiconductors and the logic cannot be created without AIs. So if we want to make a very good AI, the logic computers or semiconductors, we need to use AIs these days, especially these days, right? We have these difficulties. Okay, maybe I don't have so much time, right? Okay, then yes, in the Robotic Research Institute in Waseda University, I'm working there, and yes, and these days, I'm in my laboratory. I'm rather working with not a rigid robot, but a soft robots using a soft materials and soft actuators and soft sensors, like human or living creatures. Okay, and then maybe let's see. Okay, the one example is the 3D printed biomimetic fingers. Okay, you see, we are printing each parts of human-like fingers by deferring to the 3D model of a real finger that consists of ligaments, bones, tendons, muscles, and so on. And then these days we can print different materials at once. So we print them to make a finger. Then this is articulation with an artificial muscle to move like a human, very flexibly, like this. See, right? What is the difference between the rigid, machines and the soft machines? For when you make once you make rigid machines with the geometry of machine structure, then we have a rigid bar and the motors, rotating motors. Then, for example, the path can be all calculated mathematically, geometrically, right, with a rigid robot. But in the case of the soft robot, for example, our hand, our junction is not rigid. We can move very flexibly with one junction. So this means that when we locate this hand here, the location of the elbow or shoulder can be differently, defined or placed like this. In the case of the rigid robot, it won't happen. Every motion or moving path can be geometrically calculated. But in the case of the soft robot, it is not like that. So what the idea for controlling soft tissues is to use machine learning, right? Then also the motion of the finger is realized by artificial muscle, but the control is made by a machine learning. Okay. And also we have different topics like tactile display or waterborne actuators to move in water, and or what? Many of them. We have in my laboratory. I have different topics like to replicate this one replicates the motion of the insect. Insect. This one. Yes, and also we are developing a fish robot. This is a robot, but it is made of a very soft fin, and it swims like that. And also we are working with an inchworm robot to flexibly move, to walk like this. And I briefly introduce some of the control of such robot. Okay, the first one is a talking robot. Okay, that speaks like a human. Okay, mostly you can listen to a human-like voice from your mobile phones or TVs or something, but all of the such voices are made by software method using computer algorithms. But what we are trying to do is to reproduce all mechanically like a human vocal system. Okay. And also we refer to the physical simulation. And okay, this is a robot. Okay, our robot consists of lung with an air tank and vocal cords to make a vibratory source sound, and resonance tube as a mouth, and the tongue inside, and the nasal cavity, so that the air is led to resonance the mouth tube and the nasal cavity to make a resonance characteristics. And then generated voice is listened by a microphone. This is not for singing, but listening to its voice for the comparison of real human voice. Then what we learn, what we do is to let the robot listen to its voice and also human real voice for reference, and to make an autonomous control of the motion inside the mouth to make the close sound to a real human voice. It refers to the procedure that the human baby learns its voice. Human babies get to learn the clear vocalization by the training with their caregivers or parents. Firstly, the babies only cries, but gradually the babies learn how to make sounds. But the babies cannot see inside the mouth. But for the articulation, the baby has to move the inner mouth. They are doing not to observe the inner mouth shape, but only listen. Then make a trial to make a close sounds by adaptively moving their mouth, right? This is what this robot is doing. Okay, everything is made by all mechanically. We use a silicone rubber mouth and the tongue, the teeth, and the nasal cavity with a plaster. And then the motors are settled underneath this tube. Okay, the size is the same with the human vocal cords with a length of 18 centimeters, because if you have a different length or diameter of the mouth, the resonance characteristics should be different from the real human. So we all made it in the same or close to a real human with the length of 18 centimeters and the diameter of 35 centimeters or something of the diameter. Okay, then as you see, this robot is able to make a different resonance characteristics by randomly moving the vocal tract, right? And this is the vocal cords to make a vibration with the air. Okay, then then the learning here we use self-organizing neural network, so that the input vector, which is given by the acoustic feature of vocal sound, then output is set as the articulation of the motors. So this network learns how to control the motors to be associated with the input vocal features, vocal sounds. Then the learning has been conducted, yes, for the learning. And then as a result, the robot successfully learns to vocalize. Okay, like this maybe. Okay. Here, firstly, the robot learns the pitch, the different, the pitch. Okay. After the learning of the pitch, then it starts. Okay. It sings a Japanese folk song. Maybe you don't know, but all Japanese people know this song and they recognize this singing. Yeah, it looks stupid, but this is the first one who that realized the autonomous learning of human vocal system, all mechanically and feedback control. This is the first one with all soft tissues. Yeah, no, not hard one. And this robot has been applied for the training system of the deaf people. Deaf people is not able to listen to their voice, so they cannot speak. No one will make a training of the motion of the inner mouth. So deaf people cannot speak. So by referring to the robotic motion, and then she imagined how her inner mouth can be moved by the muscle articulation. Then she makes a training with this robot. And also, vocal features are in real time mapped how close to the target voice is. Okay, each she vocalizes, the vocalized sound is mapped in a self-organizing map. Then he recognizes how the vocalized voice is different from the target one. Then by the training with the motion of the robot and the mapping of the acoustic features, she gets to learn how to make a clear voice with this robotic system. The next topic is, briefly, the robotic fish. We have developed a very soft robotic fish with a soft fin like this. But what was the problem is that the soft fin is not controllable, especially in water. Yeah, and it swings with different frequencies of the soft actuators, and the relation between the control command and the swimming performance is pretty uncertain, right? So what we try to do is to associate the control parameters with the generated swimming behavior with a neural network by using a neural network. Then it was successful. Then yes, the robot, the fish robot. Yes, it is untethered one. Yes, everything is packed into this robot, and it moves. It swings like this with a 2 Hertz flipping motion. And also maybe, yes, we have, yes, this is a slow, maybe, okay, let's see, another one. Okay, okay, maybe this one, okay. The slow flipping motion, like this. Very slow one. Yeah, 1 Hertz flipping motion, and faster. Yes, 2 Hertz flipping motion. The robot, this fish robot is able to swing with different flipping motion, and it can turn right and it can turn left at any by using the learned control parameters with the flipping motion. Okay, like this. The robot is pretty real, right? Okay, and maybe we okay, and also this is okay, maybe this is the first one. Continuum robot for flexible object grasping. Okay, we are developing also a long tail-like robot for grasping objects. Okay, like this. We construct this with flexible robot with a ball joint and the spring and pulling actuators. Okay, like this. Okay, maybe yes, like this. Yes, it can move like this. Okay, like this. It moves by pulling the tendons. But what is the problem is that when we like to put the tip of the robot in some location, there are different, possible, the shape of the robot, right? Yes. So we also apply a neural network for the learning of this flexible motion. Then yes, and then it able to grasp like this. Okay. Yes, with a different style of the grasping, like this, all learned by the machine learning. Yes. Okay. Maybe it's time to I have some other examples, but it's time to. So maybe okay. Yes. Yes. Okay. The conclusion is that I have introduced some mechanical or soft system to grow up. To learn like human behavior. Okay, yes, maybe that's all. Thank you very much. These are my research group with my students. Thank you very much.
So we have time for some question.
Yes.
Thank you for very nice presentation. I'm wondering, how do you explain? You said that this is explainable AI for your fish and human robot. How your explain tools used in this control? Thanks.
Explain is okay. I'm in my laboratory. We are also working to explain how it learns. Okay, one of the explaining method is to use a feature map, self-organizing feature map. We set the self-organizing feature map in between the some layers. Then in the feature map, some relation of the patterns are mapped in the feature map, so that the cross patterns are mapped close with each other, and the different patterns are located far with each other. By referring to the topological relation that has been automatically constructed in the map, we can see what relation the learning result is obtained.
Okay, makes sense. So you mean you can identify what features find by the machine learning?
Yes.
Yes. And
yes.
How do you use this information to optimize the control or optimize the learning?
Okay,
learning process.
I see. Okay, from the viewpoint of the optimization, so far, in the application of the control of soft robots, we do not think of that. We do not consider the optimization because in the human behavior, I don't think we have optimized motion or behavior. Humans are doing some behavior without explanation, right?
Yes.
So what is good for the soft robot like fish or a rolling ball or a speaking robot? What is the result is how human understand it, how human considers satisfied or something. So satisfactory or the satisfactory by human can be one measure for the evaluation of the results. We think.
Agree, yeah. But yes. I think maybe if we can get the explainable information, maybe we can help accelerate the learning. It is possible?
Yes,
for
it
example,
can be possible.
For the human, for the baby, if we know how the baby learn it, maybe
yes.
we can give more, do some optimization, make the baby learn it fast.
Yes. As I just mentioned, okay, here, let's see. Okay, the speaking results. Okay, yes, maybe. Okay, this one. Okay, the robot learned the transition from R voice to E voice. Okay, the motion of the articulatory motion smoothly moved to R to E. So we can recognize that this learning was successfully made. For example, this is a performance from R sound to E, R, E, E. Okay. In the case of human R to E voice, from R voice we open the lips and the deep location is narrowed. But on the other hand, E sound, E is pull your lip, and the deep side opens. So this motion has been automatically obtained by the robot. So this kind of the motion is understood by the satisfactorily obtained. Yes. So this is one of the evaluations that we have for the after the performance of the learning. Is it okay?
Yeah. Okay. Thank you.
Thanks for that nice talk. I was wondering about the dynamics. When we have neural networks, that is a mapping of the inputs and the outputs.
Yes.
So how are you characterizing the dynamics with the neural network? So let's say the sampling time of the system, or how are you considering the sampling time of the system or the time constants of the system within the neural network?
I see. In fact, it depends. For example, this speaking robot, sampling frequency is set as the voice sampling ratio. Like in this case, I see 10 kilohertz for the vocal sounds, and each sound is mapped into the motion of the motion of the robot. And on the other hand, in the case of the fish robot, the sampling frequency is not very fast, like video sampling rate, 30 hertz. So it depends on what kind of information to be given to the robot. It depends for the control of the robots. Yes.
Thank you so much for the presentation. Thought it was very interesting. One of the things that is interesting, as you mentioned, of using machine learning and other adaptive mechanisms to learn the model web instead of having to define the functions that you can apply to this complex problems.
Yeah.
But do you try to afterwards extract a physical function, for example, a differential equation, represent this dynamics?
Maybe we will do it. Okay. What we are doing is to apply reservoir computing method. I'm also working with a scientist of the reservoir computation, and I belong to the Department of Physics. So this kind of nonlinear function obtained by the neural network can be associated with a reservoir computation. It is all physically constructed in a reservoir. So yes, we will now working for the reservoir computation. Yes.
Okay, because I was thinking in terms of security. For example, you're moving a hand.
Yes.
And if you learn a model that has a lot of parameters,
yes,
you might not know what are all the possible outputs, and
yeah,
you might react in a very strange way in a certain moment.
Yes, that's right. Yeah.
You have a human, and suddenly, now I was seeing all these videos in China of suddenly the robots following people or attacking people. When this can happen, and given input parameters that are not known.
I see. Yeah. In fact, it depends on how much complexity the robot will do for dealing some objects. Just to make some gestures, it's okay. But if you like to, manipulate some, for example, mobile phone or some chopsticks or something, you need much more, much complex, articulations of the finger, right? So this is what we are trying to do, not just simply, motion, but also to manipulate something for supporting human.
Okay, thank you.
Thank you very much.
I think that then we can thank again the speaker. I'm pretty sure that there are a lot of other curiosities that you would like to ask to Professor Sawad, and so I strongly invite you to do it after closing this session. As a matter of fact, as I always say, the BrIAS Thursdays events do not end with the 2 formal presentations, but you are invited to enjoy a second coffee, chat with the people present, try to create connection, try to have crazy ideas and to develop them. So I strongly invite you to stay with us a little bit longer. Instead, we will say goodbye to the people online that cannot join us for a coffee, not even virtually. So again, thank you for being with us today, and see you next Thursday for the next 2 very interesting seminars. Have a good afternoon.